Hi, everyone. So we're going to go ahead and pick up where we left off in class on Monday. So on Monday, we had talked about basically acetylide substitution, where we were able to deprotonate a terminal alkyne and then extend the carbon chain through acetylide substitution. So today we're going to continue looking at alkynes. So we're going to start by looking at basically a reaction or a series of reactions that allows us to prepare alkynes from alkenes. Okay, so we're going to title this alkene to alkyne synthesis. Okay, and the new reaction we're going to learn here is something called double dehydrohalogenation. Okay, so double dehydrohalogenation. Okay, so as that name implies, dehydrohalogenate. So I'm going to remove a hydrogen and a halogen. So dehydrohalogenate means I'm going to remove those two atoms, and I'm going to do that 2 times. So let me show you the overall alkene to alkyne synthesis procedure, and then we'll talk about that reaction, double dehydrohalogenation, in a little bit more detail. Okay, so if we were just to start with a generic alkene here, and the first reaction we're going to do is, well, we need to add the 2 halogens that we're going to then dehydrohalogenate with. And so we know how to add 2 halogens with X2. So this is a reaction from chapter 6 that we already spent time talking about. Remember that this reaction gives us anti-addition of our halogens across the carbon-carbon double bond. Okay, and then our new reaction, this is the dehydrohalogenation. Okay, so for now, I'm just going to write the conditions as base, and then I'll say a little bit more about that here in a second. Okay, and so this is the double dehydrohalogenation step. So double dehydrohalogenation. All right, so basically what we're going to do is we're going to remove HX twice to form first a double bond and then a triple bond. Okay, so let's go ahead and look at the products of this reaction then. So let me count my carbon chain so we can follow what's going to happen. So the products of this reaction are our alkyne. Okay, so the 2 carbons, so specifically in this example, carbons 2 and 3, those are the 2 carbons that were bound to the halogens, and those are the 2 carbons that are going to end up being part of the triple bond in the product following dehydrohalogenation. Okay, and so what are the conditions for dehydrohalogenation? Okay, so dehydrohalogenation. All right, so the first condition would be NaNH2 in either 2 equivalents or 3 equivalents. And I know we haven't introduced the term equivalence yet, so I will do that here in just 1 minute. And then our solvent is ammonia. Okay, and so that is our solvent. All right, so that's one set of conditions, NaNH2 and NH3. So we can see that there's a base present. The other set of conditions is KOH, so potassium hydroxide, ethanol, and heat. Okay, so delta, this is also something we have never seen before, is heat. Okay, so let's talk about equivalence for a second, and then we'll come back for full circle and talk about the dehydrohalogenation. Okay, so this EQ. Okay, so EQ stands for equivalence. Okay, and this is related to stoichiometry. Okay, so 2 equivalents would be a 1-to-2 mole ratio, okay, where the 1 is your starting material. So you have 1 mole of your starting material to 2 moles of whatever the reagent is. Okay, so when we're saying 2 equivalents of NaNH2, that means for every 1 mole of our dihalide we would have 2 moles of our NaNH2. Okay, or if we had 3 equivalents, that would mean we have 3 moles of base for every 1 mole of our dihalide. Okay, and one thing I also want to mention before we jump into the mechanism here would be to, just to reiterate this NaNH2, this sodium amide, realize now that that's the reagent that we used in the previous reaction to generate acetylide, and it's the reagent we're using now for a different purpose. Okay, so you need to keep track what we're doing. Are we deprotonating to make acetylide? Are we doing the dehydrohalogenation to form the alkyne? Okay, so let's talk about the mechanism of dehydrohalogenation. Okay, so here's the mechanism. All right, so let's just look at that example that we saw a minute ago. So we're going to take X, and it doesn't matter if X is Cl or if it's Br. So in this particular case, okay, so internal alkynes, okay, so when we're going to make internal alkynes, we require 2 equivalents of base. Okay, and we'll see why that is in the mechanism. Okay, so terminal alkynes, so for generating a terminal alkyne, requires 3 equivalents of base. And we'll see why that is when we look at the mechanism. Okay, so in this case, let's break it up into each step. So we're going to look at the first step, so NaNH2 with 1 equivalent. Okay, so here's our first equivalent of NH2 minus. All right, so what we're going to see here is we're going to remove a hydrogen at the same time that we're removing the halogen. Okay, so I'm actually going to get rid of stereochemistry here to simplify this. And what I'm going to do at both positions, sorry to erase, is I'm going to draw in the hydrogen and the halogen at each one of those carbons. Okay, so what we're going to see is that the base is going to do what bases often do, which is take a proton. Okay, so I'm going to take this proton here. And what we're going to see is that instead of just generating the conjugate base as a carbon anion, we're going to use those electrons to kick out the halide. Okay, so this arrow here, so this arrow is telling us that I'm taking electrons from that hydrogen carbon bond, I'm generating a pi bond, and I'm kicking out that X minus or that leaving group. We've seen that terminology before. Okay, and so what does that give us initially? So that gives us an alkene intermediate. Okay, and then we've also generated our halide leaving group here. Okay, so that is what happens if we had a 1-to-1 mole ratio, but now we're going to add our second equivalent. Okay, so it's still reading as NaNH2, and now this is our second equivalent. Okay, and so we're basically going to repeat that step. So the amide is going to take up that proton, we're going to generate a pi bond, and we're going to kick out the leaving group. This now has formed our alkyne. Okay, so we've now seen why this is called double dehydrohalogenation. In each step, we are dehydrohalogenating, and we're doing that 2 times. Okay, so let's look at one example and one more example of an internal alkyne, all the way from alkene to alkyne in that series of steps, and then we'll talk about terminal alkynes and why they require 3 equivalents. Okay, so here's our example. So what we want to do is essentially convert this alkene into the corresponding alkyne. Okay, so we would use our halogenation conditions like Br2 in our inert solvent. That gives us our dihalide. And here, the stereochem doesn't really matter because we're going to get rid of those stereocenters anyway. Here, I'll just write racemic. Okay, so let's count our carbons here. This is a time that I would really encourage you to count carbons so that you don't lose any carbons as you're going through the reaction. And you'll realize what I did is I added 1 too many carbons, so I need to redraw that. Okay, so we have 5 carbon starting material, 5 carbon product of this step. Our alkene was between carbons 2 and 3, and our bromides are at carbons 2 and 3. And now we can do our dehydrohalogenation. Okay, and so how this would read is we would have NaNH2 in 2 equivalents, and then our NH3 ammonia as a solvent. And so then the product of this step would be the alkyne between carbons 2 and 3. Okay, so this shows us how we can put together a series of reactions to basically, go from an alkene to an alkyne where there isn't a direct reaction that does that in a single step. Okay, so let's talk about the formation of terminal alkynes quickly. Okay, so formation of terminal alkynes. Okay, so let's look at an example, and through the example, we'll highlight why we need 3 equivalents. Okay, so something that would give us a terminal alkyne would be if we had a terminal alkene or an alkene at the end position. So again, I'm going to start this off with bromine in our inert solvent. And here we have our racemic dibromide. Okay, and so now the conditions are that we need 3 equivalents of NaNH2. We'll still use an ammonia solvent. And there's one other new thing. We're going to have a workup step. Okay, so this is called a workup step. Workup. And we'll describe what the workup step is through the mechanism. Okay, so predicting the products is no different here. We just need to keep track of the slight variation in the overall reagents and conditions. Okay, so let's count our carbons. So I should have a 5-carbon chain in the product where I have an alkyne between positions 2 and 3. Okay, let's make that a little bit longer. Okay, and so we can see the product. Product's not really any different, between the previous example that we had, up here with the internal alkyne versus the formation of the terminal alkyne. But we'll see in the mechanism why we require the 3 equivalents of base. Okay, so in the mechanism. So the mechanism starts off in the same way. We're just going to have to realize, something about one of the intermediates when we get there. I draw that upside down. I'll keep it the same way so that it's easier to follow. Okay, so here's our dihalide. Again, I'm going to draw in the hydrogens at those positions so that we can write the mechanism. Okay, so we're going to use our first equivalent of NH2 minus. All right, so it's going to pick up one of the protons. We're going to donate those electrons and kick out the bromide. That's going to form the alkene. And I didn't mention this before, but it doesn't really matter which hydrogen and which halogen you remove first, whether it was on the carbon on the left or the right, respectively. Okay, so there was our first equivalent of NH2. Now let's react with our second equivalent of NH2. All right, so that amide is going to pick up, the proton. At this position, we're going to donate electrons and kick out the leaving group. Okay, and so now we've formed what looks like our product. Okay, but notice what we've done here, right? We have generated an acidic proton. Okay, so we've generated an acidic proton. Remember that terminal alkynes can readily be deprotonated by NH2 minus, by sodium amide. And so what the situation is that I need to add enough base to account for the formation of the acidic proton. Otherwise, you would run out of base because not all the molecules are reacting at the exact same time. Okay, and so that just basically gives us a buffer. It allows us, not a buffer in terms of solution, but in terms of the amount, it allows us to account for the formation of this acidic proton. Okay, so the third equivalent of base then is actually forming the acetylide anion. Okay, so we form acetylide. All right, and so this is actually the product of 3 equivalents of NaNH2. And now we can see why it might necessitate that H2O step. If you want the terminal alkyne with the proton attached, then you need to have this workup step. So workup usually means that you're doing some acid-base step to get to your neutral product that you want. Okay, so this would be our H2O. This is our workup step. Okay, and that just gets us back to the terminal alkyne, as we'd want. All right, but we could also do acetylide substitution here, so I'll just make a note of that. So if you varied that step, rather than having water as the workup, you could have added in some alkyl halide and done acetylide substitution, as we talked about on Monday. Okay, so this highlights the necessity for the 3 equivalents. So really what you need to keep track of is if you're making an internal alkyne versus a terminal alkyne, that will slightly vary the conditions for dehydrohalogenation, although the overall mechanism is similar between the 2 of them. Okay, I'm going to pause, and when I come back, I'm going to talk about electrophilic addition to alkynes, and these are going to be our parallel reactions to alkenes. So you might take a few minutes and just take a look at the reactions of alkenes and just have them fresh in your mind, because we're going to see a lot of parallels between this, what we're about to learn, and what we learned in chapter 6. All right, everyone, I'm back to talk about electrophilic addition to alkynes. Okay, so as I mentioned, these are going to be parallel reactions to the alkene reactions that we learned in chapter 6. So we're going to see some familiar reagents. For example, our first reaction is going to be the reaction with X2, the halogen. And then we're going to look at hydrohalogenation with HX. and then we'll consider some hydration reactions of alkynes. Okay, so our first reaction then is going to be the reaction of alkynes. Reaction of alkynes with X2. Okay, and again, X is going to equal chlorine or bromine. All right, so let's look at the overall scheme of this reaction. Okay, so we're going to have our alkyne, and for now I'm just going to indicate, internal alkyne, and we'll talk about internal versus terminal alkynes as we go through some examples. All right, and so we have 2 pi bonds to react as part of our alkyne. So remember that our pi bond was 1 sigma and 2 pi bonds. So for that reason, we actually have 2 sources of electrons that we can utilize in these electrophilic additions. So we actually are going to revisit the concept of different varying equivalents or varying the stoichiometry. So I'm going to break each of these reactions up into what if we react just 1 pi bond with 1 equivalent of our reagent, or what if I react both? Okay, so let's take a look at if I were to react X2, only 1 equivalent. Okay, so what we're going to see is we generate this species. And I'm going to jump back into line angle formula just because it's easier to write out. Okay, so notice how I have essentially anti-addition of X2 across the carbon-carbon triple bond. So I've only at this point reacted 1 of the pi bonds. Okay, and now if we see, the product of this step, it's just an alkene. Yes, it has halogens on it, but fundamentally it's still an alkene. And so I could add a second equivalent. So now we'll have 2 equivalents total. All right, and then I'm just going to follow addition of X2 across an alkene as we already talked about. So the product of this reaction then would be basically where I've ended up with this tetrahalogen species, okay, where each carbon of the carbon-carbon triple bond now has 2 new sigma bonds to the halogen. Okay, and we're really not going to focus on the mechanism of this too much. We already talked about the mechanism of this to a great detail when we were in chapter 6. Okay, so we'll see some similar players if you were to consider the mechanism. You go through a bridge-like species from the alkyne starting material to the dihalide alkene product. And then the second equivalent of X2 follows the exact same mechanism as we learned in chapter 6. So I'm going to spend some time just considering this reaction. Okay, and one thing to note is look at these 2 carbons. Okay, so think about them in terms of stereochemistry. If both of those bonds to the halogens are to the same halogen, in this case, we won't have to worry about stereochemistry. I will introduce one example where we could introduce stereochem, and that would be if we varied the halogen between the first and the second equivalent. And we'll look at an example of that here in a minute. Okay, so here's our first example. Oh, and maybe before we do that, we should take a look at the regiochemistry. Okay, so we actually won't see the regiochemistry, or this is not a regioselective reaction, because both carbons of the alkyne get the same bonds to halogens in the products. Okay, so there is no regioselectivity to discuss in this reaction. Okay, so example. All right, so in these alkyne reactions, again, I strongly encourage you to number your carbon chain so you don't lose any carbons along the way. Okay, so we're going to do this with bromine, Br2. We're going to have our dichloromethane as our solvent, just like in chapter 6. And in this case, let's just show 2 equivalents right off the bat. So we could show the intermediate. Okay, so we would have our 5 carbon chain. And again, I'm going to count my carbons to keep track. Okay, so between carbons 2 and 3, that's where my alkene should be, and my dihalide. So each position of the alkyne takes 1 bond to the bromine, and then we can continue on through that. So this would be the product of 1 equivalent, and we could continue on through the reaction with the second equivalent. And then in the end, both carbon 2 and carbon 3 end up with 2 new bonds to bromine. All right, and let me count my carbons so that you can follow them in the products. Okay, so carbon 2 and 3 were the carbons of our alkyne. They are now the positions that have taken the 2 new bonds to the halogens. Okay, so let me look at one last example. As I told you, let's consider an example where we might have to worry about stereochemistry. Okay, so let's consider this reaction. Okay, and so I'm only going to number the carbons of the alkyne because that's where all the reactions happening. And I want you to consider if I took bromine in step 1, 1 equivalent. And then I took the product of that one equivalent of bromine and subjected that to chlorine, one equivalent. Okay, and so let's just draw the product without stereochem and just ask, have we generated chiral centers? And then we'll worry about, figuring out what the absolute configuration of the chiral centers are. All right, so carbons 1 and 2, those are going to be the carbons that are going to end up with the bonds to the halogen. So there they are. So let's go ahead and fill in those positions. Okay, so carbon 1, I'm going to fill the hydrogen in so that I can indicate all the positions here. So carbon 1 has a bond to bromine and chlorine, as does carbon 2. Okay, so notice how we've generated 2 chiral centers. Okay, so we have 2 new chiral centers. So 2 new chiral centers. Okay, so we have 4 possible stereoisomers, right? That's how many are possible, but how many would we actually observe? So both steps of the reaction are stereospecific for anti-addition. So let's go ahead and consider what would be the product after one equivalent, and then think about then what the actual stereochem of the products are. Okay. So the product of step 1 would be anti-addition of bromines across the alkyne. And now when we do anti-addition of chlorine across the alkene, we're going to follow the rules of anti-addition as we learned them back in chapter 6. Okay, so one way we could draw the products then is to keep, the atoms that were along the horizontal in the same orientation. Okay, and then I would add my chlorine's anti. So if I'm choosing to put the chlorine at carbon 2 on a dash, that means the chlorine at carbon 1 would have to be on a wedge. So notice how both the chlorine with respect to each other and the bromine with respect to each other are anti. So I would have that product and it's an enantiomer. Okay, and I won't observe any of the syn addition products because that's not consistent with the mechanism as we've talked about. Okay, and in this case, I'm choosing to show the hydrogen in plane because it allows me to easily see the anti-addition between the chlorine and the bromine. Okay, and so we would get this racemic mixture of anti-addition products. Okay, so the next parallel reaction we're going to consider of alkynes is going to be the reaction with HX. Okay, so let's consider the reaction of alkynes with HX. Okay, so again, we're going to have a situation where we could have either react one or both of the pi bonds of the alkyne. And now we're actually going to have a regiochemistry issue to talk about, okay? Because each carbon of the carbon-carbon triple bond is going to end up with a different bond to a different atom, okay? So let's take a look at that and then we'll consider some of the mechanistic issues. Okay, so we're only going to be able to see the regioselectivity with a terminal alkyne. You can do this reaction with an internal alkyne, and we will show examples of that once we've talked about the mechanism, but we can only see the regiochemistry or the regioselectivity with a terminal alkyne. Okay, and that's because that carbon, the carbon on the left, is more substituted, whereas the carbon on the right is less substituted, right? Because it's bound to hydrogen, whereas the carbon on the left is bound to a carbon. Okay, so the only time we can observe regioselectivity in alkyne reactions is if we are actually using a terminal alkyne. Okay, so let me go ahead and think about then this reaction. So we're going to treat this with HX, and again, let's break it up into the 2 respective equivalents. Okay, so if I react with just one equivalent, I'm going to end up with adding HX across the carbon-carbon triple bond. Okay, so notice how I have added an X to the more substituted side and an H to the less substituted side. Okay, so I'm basically following Markovnikov addition across the alkyne. Then I can repeat this step with our second equivalent of HX. Okay, so following the second equivalent, I'm really just following the reaction that I learned in chapter 6. All right, and I'm going to draw the hydrogens in here just so that we can see them. So notice even with the second equivalent, we've added another X to the more substituted side and another H to the less substituted side. So this is a regioselective reaction for Markovnikov's halide, okay? And again, the only time we can see the regioselectivity is if we are using a terminal alkyne. So let's look at an example to talk about the mechanism, and then we'll look at an example of an internal alkyne. Okay, so here is our terminal alkyne. Let's react this with HBr in two equivalents. Okay, in the mechanism, we'll break it up and talk about each equivalent independently. Okay, so the overall product of this reaction we would expect to see would be the dihalide at the more substituted position of our alkyne. Okay, so we have carbon 1 and carbon 2. We can see that carbon 1 now has 3 hydrogens, carbon 2 has 2 bonds to the bromine. So we've added HX or HBr across the triple bond twice, adding the halogen to the more substituted position in each case. And notice how if both halogens are the same, so if I use two equivalents of the same HX, I'm not going to generate a chiral center. So we can see that this carbon here doesn't constitute a chiral center because there's 2 bonds to the same atom, which is bromine in this case. Okay, so let's talk about then the mechanism of this reaction. Okay, so this mechanism follows the mechanism of HX with an alkene that we talked about in chapter 6. Okay, so our first equivalent of HBr, we're going to have the pi bond act as a nucleophile or as a base, and it's going to be protonated, and we're going to generate a carbocation. And then our halide that we generate is going to then come back and attack that carbocation. Okay, and so one thing to mention about that carbocation is we're adding it to the, or it ends up at the more substituted position because of stability. All right, so let's draw the product of that step. So this would be the product after one equivalent. Okay, so product after one equivalent of HBr. Okay, and so now we can repeat that step. Okay, so let me just redraw that in a new line, and let's consider the reaction with the second equivalent of HBr. Okay, so now the mechanism really shouldn't be surprising because we're basically just taking an alkene and reacting it with HX. Okay, but there is one thing that I want to mention as it relates to this carbocation. Okay, so I'm going to put this carbocation at the more substituted position. Okay, so notice the position of the carbocation at that more substituted carbon. But there is something else that's influencing the stability of that carbocation at that position. Can you think about what that might be? Remember that the halide has lone pair electrons. Okay, so this is actually resonance stabilized. All right, so this is a resonance stabilized carbocation. And why that matters is because it basically means that wherever you've added the first halogen, the second halogen must follow, because it's that first halogen that is stabilizing the carbocation through resonance. So let me just show the resonance structures down below. Okay, so wherever the halogen first adds, that's where the second halogen must go, because this halogen is stabilizing that carbocation. Okay, so we can see that this is a resonance stabilized carbocation. And now the bromide that I generated in that step can act as a nucleophile, and that's going to give me the product overall of this reaction. Okay, so we can see in the mechanism then, again, we're going through familiar intermediates like carbocations. And again, one of the most important facets is that this carbocation demonstrates why wherever the first halide goes, the second halide must follow because of that resonance stabilization that we talked about. Okay, so let's look at one or two examples of this. So let's look at one example where we vary the halogen. So we'll use HCl in one step and then HBr in the other step, and then we'll look at an internal alkyne. Okay, so in step 1, let's do HCl, one equivalent. In step 2, we'll do HBr in one equivalent. Okay, so we're still going to add both halogens to the same carbon. So in this case, carbon 2 is the more substituted position. Okay, so there's our 4-carbon chain. Let's get our numbers on there. Okay, so carbon 2 is going to end up with a bond to chlorine and to bromine. Notice now carbon 2 is a chiral center. I have methyl, isopropyl, chlorine, and bromine. Okay, and remember that when we add into carbocations, we end up with racemic mixtures. Okay, so I would have that stereoisomer, and then it's an enantiomer where the bromine is on a wedge and the chlorine's on a dash. Okay, so we could generate chiral centers in this reaction if we're going to vary the halogen between step 1 and step 2. Okay, and then our last example for this reaction, and then I'm going to conclude part 1 of this lecture, and then I'll start a new video for part 2. Okay, so our last example, let's look at an internal alkyne. Okay, so let's look at an example of an internal alkyne that is not symmetric. Okay, so let's just do this with HCl in 2 equivalents. Okay, so if I'm comparing carbons 2 and 3 in terms of their substitution, they're similarly substituted. So either carbon 2 or carbon 3 could bear the carbocation. But remember, when we looked at the mechanism, wherever the first halide goes, the second halide must also follow because of the resonance stabilization of the carbocation. So the products of this reaction then, I'm going to get 2 different regioisomers. I'm going to get the dihalide at carbon 2, and I'm going to get the dihalide at carbon 3. Okay, so these are my 2 regioisomers that I get coming out of this reaction. And again, that's because for an internal alkyne, we can't observe the regioselectivity because as we see, carbon 2 and 3 are similarly substituted. So you might be wondering, well, you know, this ethyl group is bigger than the methyl group, maybe that influences somehow the reaction. Okay, but remember that the bond angles at alkynes are 180 degrees, and so the sterics felt by varying size substituents is not that great because of those wide bond angles. Okay, so I'm going to conclude part 1 of this session here. When we come back, the second half of lecture, the second part of lecture, I'm going to talk about the hydration reactions of alkynes. So we'll be seeing similar reactions to oxymercuration and acid catalyzed hydration, and then also hydroboration oxidation.